Let's get this show on the road. Hello, everyone. Hope you're well. You'd also like to petition a question on the quiz? What do you mean?
So for one of the questions on the quiz, I feel like there were multiple answers. I can write this in an email later today.
Oh yeah, just maybe even do does the quiz have a regrade thing on it? You can do that as well, but I'll see.
It doesn't. I can send a screenshot and everything.
Was that
It's
the
fine.
one with the ellipse? Is that the one?
No, it was x squared minus y squared equals 0.
Okay. I don't remember what the choices were, but what do you mean?
So
what do you think were the multiple possible answers for that one?
it could have been none of the above, and it also could have been a hyperbola.
Oh, no, it cannot be a hyperbola for sure. So it was definitely none of the above. For a hyperbola, you have to have a 1 on the right side. You can't have a 0 constant on the right side, right? Because if you have the x squared minus y squared equals 0, you could bring the y squared to the other side. You'd have x squared equals y squared. Take the square root of both sides, you get x equals plus or minus y. You'll actually have two straight lines like going into x. So the graph of it would actually be two straight lines like this. It's definitely not a hyperbola. There was one that I do believe there was a typo. There's one with like an ellipse, something with an ellipse. And there was a typo on it. So I know
what was the typo?
There are probably a few.
I know there was a couple questions that mentioned.
What was the typo, by the way? Show it to me, by the way.
Well, not right now. Right now, we need to get back on track with what we're doing. So we'll worry about the quiz afterwards, some other point. But so far, I know that there was one typo that I noticed. Anyway, let's actually let's jump right back into it. So here's what we were talking about last time. We pretty much developed the dot product. So last time we spoke about the motivation behind two things that we want to talk about next. One was the dot product, the other was the cross product. So the idea is if we're going to be in 3 space and we're going to want to do calculus in 3 space, we have to figure out certain things that would allow us to do calculus. Things like if you have a surface, we need to be able to dissect it in 2 dimensions. So we need to have some 2-dimensional dissections. So the obvious choice would be dissecting things in terms of rectangles because we're used to building up things with rectangles in calculus. So I have to figure out a way to find things like the area of these rectangles so that we can measure these dissections and build up to integration. We had to find some measure of how these patches were tilted, right? Because this is what we'll need to do calculus. We need to talk about the direction in which things are slanted. We need to also be able to talk about being able to dissect our input space and then measure the area that it's going to result from that, which in Calc 1, we had to measure the length of the subintervals, but now we don't have subintervals anymore. We kind of have these subspaces, 2D spaces in Calc 3, and it actually can go higher. So we needed to know all of that. So it became very important for us to be able to figure out the area of a patch, which if we run vectors along the edge and the angle between them is theta, we can figure out the area by this expression here. We also figured out a way to actually get to what theta is. We can use the law of cosines to develop this. We also noticed that to actually talk about the direction in which a patch is slanted, an orthogonal vector, a vector that's orthogonal to the 2 vectors, is going to be the guy that we care about. So for example, if I have a vector here that's A, and I have a vector here that's B, then a vector that's orthogonal to A and B can talk about how this patch is slanted here. And so we understood that in order to even find that, we need 2 vectors to compare these 2. And that's actually what we're going to get to today eventually, actually. But then when talking about the error problem a little bit more, we realized that there was this expression that keeps popping up when we try to find the area of the parallelogram spanned by two vectors, or the angle that is formed by two vectors. This expression keeps popping up, so we gave it a name. We call this the dot product. We call it A dot B. And this is what's called the dot product of two vectors. The dot product is a scalar. So it's a scalar quantity. You take A dot B. This is how you find it. A1 times B1 plus A2 times B2 plus A3 times B3 all the way up to dot, 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 plus AN times BN. It's also true that A dot B is equal to the magnitude of A magnitude of B cosine theta, where theta is the smallest angle in between them. So we also looked at some properties here, just glanced at those. Now, this specifically says it works in a three-dimensional space, but these properties actually work in higher dimensions as well. The dot product is something that can work in any dimension. Okay. We also found that there was something called orthogonal. This is just another way of saying perpendicular, but in a higher dimensional analog of being perpendicular. And we saw that the dot product can indicate when two vectors are orthogonal if the dot product returns the zero scalar. So if the dot product is zero, we are orthogonal. Then we just jumped into some examples. We computed the dot product, boom. We found the angle between two vectors here, boom. And we had some more examples to finish up. So let's actually just finish those guys up. We're going to talk about some important applications of a dot product here. Someone just come in. And then we'll actually move on to the next topic. So let's actually jump into that. So here are two vectors. Show that the vector 1, 3, 5 and the vector -5, 0, 1 are orthogonal. So to show that a vector is orthogonal, two vectors are orthogonal, all you need to do is show that the dot products give you the zero scalar. So notice that if I take 1, 3, 5 dotted with -5, 0, 1, this is 1 times -5 plus 3 times 0 plus 5 times 1, right, as someone wrote in the chat there. And you'll notice that that gives you 0. So here, dot product is 0. This means the vectors are orthogonal.
That's right.
And we have Jason's approval, so we know we're fine. All right, and that was it. Here's another example. And these are just examples, very computational examples using dot products. Find the dot product if the magnitude of A is 2, the magnitude of B is 3, and the angle between them is pi over 4. So I have two vectors. Here my A has magnitude 2. And then I have a B, which is magnitude is 3. And I know the angle between them is pi over 4.
Radians.
Right.
What you would do actually, if you know the formula is cosine theta equals vector A times vector B over the magnitude of vector A times the magnitude of vector B, like, you know, and
right.
therefore
that's correct. But one thing I would say is be careful. Don't call it times. Actually call it dot. Right. So specifically use the phrase A dot B. Don't say times.
Okay, because I just saw the black dot. The black circle.
Yeah, so it's specifically the dot product. So it's not multiplication like you would do with numbers. So A dot B is the magnitude of A, magnitude of B, cosine theta. So here we'd have 2 times 3 times the cosine of pi over 4. And so that is 2 times 3 times radical 2 over 2.
You get 3 radical 2.
Exactly. So
that's your final answer.
Mm-hmm. And
Does
so,
anyone agree?
Again, be careful with multiplication. Don't use the word times when you're talking about vectors. You really want to say either a dot or cross. As we'll talk later today about the dot product versus the cross product, because technically speaking, there is no multiplication of vectors in the way that you would multiply numbers. So you want to be careful with that concept here. All right. Suppose I know that A equals A1 comma A2. Find a non-zero vector B that is orthogonal to A. Now this one is just, I mean, it's not particularly instructive. It's just a little cute thing. Later on, I'm going to derive something for you guys, and I'm going to mention that there's another way to actually do it. And so this is kind of suggestive of what that other way is going to be. So I'll just do it for you. Here's something that if I'm given A1, A2, what I can do is to create something that, of course, if I want to be orthogonal, I need to make sure that the dot product is 0. To make sure that something has dot product 0, what I can do is I can switch the positions of these guys and then make one of them negative, right? Or I could have done it the other way. So A2, A1, and make the A1 negative. What you'll realize here then, if I take A dot B, you would just get A1, A2 dot B1, B2. And in this case, this is, I should put this in, minus A2, A1. So what you'll get here is minus A1, A2 plus A1, A2, and that will always be orthogonal. So for example, if I have the vector 1, comma 2, then I automatically know the vector minus 2, comma 1 is orthogonal, and so on. So that's just a cute little thing. So this is sort of the nice aesthetic choice, and I'll refer to this. This is the aesthetic choice. It's not the only choice that you could make, but it's the aesthetic choice. Not an official term, I'm just calling it that. But later on, I'm going to mention something where, oh, you can make the aesthetic choice. And I'm talking about making a choice like this. Just rearrange the things in such a way and just put negative strategically on them. Don't scale anything or anything like that, but put a negative on some of the components, and it'll cause things to work out very nicely, right? So from here on out, this will be known as the aesthetic choice. I'm going to mention this at some point later on, but yeah. Now here's an important thing, and we will be using this to derive some other things as well, but vector and scalar projections are actually super important ideas when it comes to vectors. And we're going to talk about what these guys are, the vector and the scalar projection of two vectors. Okay, so this is a scalar projection here. So here's what a vector projection is. Let's say I have a vector A and a vector B. And what we want to do is, like, we imagine that we're shining a light. Like there's a light bulb out here. Right? And it's shining a light. And essentially what's going to happen, it shines a light perpendicular and it projects the shadow of one vector onto the other vector. Right? Now, if I find the vector that runs along that shadow, so the vector is parallel to A, running along A, and it only runs for the length of that shadow. That vector is called the vector projection of B onto A, because I project the shadow of B onto the vector A. This is, so that red vector here is called the vector projection, and that is, the notation is PROJ. Right? So that's the projection of B onto A. That's the notation. Then if I only mention the shadow and I measure the length of the shadow, then that is called the scalar projection of B onto A. Now, of course, because with trigonometry, if I have this angle here, and this is a right triangle, I can actually figure out that the length of the base here is just going to be the magnitude of b cosine theta, right? Just by SOHCAHTOA, right? Now, and that's called the component of b onto a, or it's called the scalar projection of b onto a. So the scalar projection is a scalar. It's literally a magnitude. It's a length. It's a signed magnitude. It could be positive or negative depending on what the value of theta is, but it's really measuring the length of the shadow. Whereas the vector projection is measuring the actual vector. Now, of course, let's talk about the component here for a second. If I look at the component of b onto a, that is going to be the magnitude of b cosine theta. But here's what you notice you can do. You can actually, to write this a little nicer, to have a little nice formula for this guy, what I can do is I can multiply and divide by the magnitude of a. You might say, why would you multiply and divide by the magnitude of a? Well, because this expression here, the magnitude of ab cosine theta, is an expression that I actually know about. That is the expression for the dot product. So this means I can write this, the length of this shadow of projecting a vector b onto a vector a, the length of that shadow is going to be given by a dot b over the magnitude of a. Okay, and that's called a component. And yes, it can be plus or minus. So this is plus or minus the length of the shadow. Perpendicularly projected onto A. Okay, so that's called the component of B onto A, and it is just, it's called a scalar projection because you're really measuring a signed magnitude here. That leads us to this equation here. So the component of B onto A is A dot B divided by the magnitude of A. Now, if I want to find this vector, the vector projection, notice that that vector is parallel to A, but it has the length of the shadow, that's the component. So in order to find the red vector, what we can do is first find a unit vector in the direction of A, and then multiply it by this magnitude over here, and that will actually give me a vector of this length pointing in the direction of A. And so that's what this is about. So if I take the component and then I multiply it by a unit vector, the vector A divided by its magnitude, we saw last class that that gives us a unit vector. Multiply that by the component, I get what's called the vector projection. Okay. Now we are going to see these in some applications later on. In your future classes, you're going to see even more applications, but we're going to be using these in some very specific applications. So let's actually just do an example of those guys. Find the vector and scalar projections of B onto A. So here I have a vector B. That is used to find the value of the projection. What is used? I don't know what the that in your comment refers to. Oh, yes, the first equation is used to find the scalar projection. You'll also notice, remember A dot B is a scalar. So when you take A dot B and divide it by a magnitude, that gives you a scalar quantity because it's just one magnitude divided by another. Here though, A divided by the magnitude of A is actually a vector. And then you multiply the vector by a scalar. The result is another vector. So this is the vector projection. So the second equation gives you the vector projection. The first equation gives you the scalar projection. And you should know these equations. All right, so that was B. Let's say I also now have A. Say this is A over here. And essentially what I want to do is I want to project this guy down. Now I will create another vector, which is this red vector that goes from here to here. So now the red vector is the vector projection of B onto A. Its magnitude is the scalar projection of B onto A. And it could have signs here depending on the orientation of these vectors. Okay, so let's say we wanted to actually find that. Well, let's start by finding the scalar projection, because you're going to use that to find the vector projection anyway. So let's worry about the scalar projection first. Scalar projection. And we're just going to apply the formula. This is the component of B onto A. This is going to be given by A dot B divided by the magnitude of A. So this is going to be 1 comma minus 1 comma 2 dot product 3 0 1. Now that's B dot A that I just wrote down, but we saw last time in the properties that the dot product is commutative, so it actually doesn't matter what order you do it in. Right here, right? A dot B is the same as B dot A. So I wrote it in a different order, but it actually doesn't matter. And then I'm going to divide, just make sure you keep track of who's the A, by the magnitude of A. So this is 3 plus 2 all over radical 10. So this is going to be 5 over rad 10.
3.301, isn't that B?
Huh?
Oh, never mind.
Yeah, B is this guy. So this is the B. This is the B right here. And this is the A over here. But A dot B is the same as B dot A, so it's okay. Now we have this. And I mean, you could simplify this a little bit, but I won't bother. So we have that guy. So now what we're going to do is, if we want the vector projection, that's going to be the component of B onto A times the unit vector in the direction of A. So that's going to be 5 over radical 10 times the vector 3 0 1 over the magnitude of 3 0 1, because my A is the vector 3 0 1. So that is going to become 1/2 times 3 0 1. And that's our guy. So in other words, this guy up here, the red vector, that is the vector 3 over 2, comma 0, comma 1/2. And its magnitude is 5 over radical 10. So now we can actually find vectors relating to each other in this particular example like that. Okay, so let me scroll up to the formulas again. Here you go. Take a picture of that. And yeah, because you should know those. And we're actually going to use those formulas to derive some things a little bit later. Okay, and that is that's all I wanted to cover for the dot product so far. Okay, so dot product of two vectors. This is the definition. So you need to know that this is in a box. You also need to know that the dot product obeys this equation here. A dot B is the magnitude of A, magnitude of B, cosine theta, where theta is the smallest angle between them. You need to remember that the dot product is a scalar. It obeys these properties. And when the dot product is 0, it means the two vectors that you dotted are orthogonal. You can also remember that dot product works in any dimensions. You can take the dot product of any two vectors in any nth dimension. Just make sure that the two vectors are of the same dimension. So you can't dot product a two-dimensional vector with a three-dimensional vector. That's not kosher. But if you have two vectors in the same dimensions, they have the same number of components, you can dot product them at any given time. The next thing we're going to talk about that's not the case, right? The next thing we're going to talk about is going to be something that only works in 3 dimensions. This guy is the cross product. Okay. So now we're going to answer, right, the cross product. Now we're going to answer the other question. Yeah, I know, I prepared this lecture. Of course I beat you to it. Okay. Now we're going to discuss the cross product. Okay, so this is discussing the other problem. So remember yesterday we figured out that if we wanted to find the sort of the amount of tilt that something is in hovering in space, what is the quote unquote slope or some sort of direction that we can describe this thing as being tilted, then yes, the cross product is 12.3, I want to say. No, the cross product is 12.4. Dot product is 12.3. I thought I had that somewhere. I believe this is 12.4. Okay. So yesterday we learned that the best way to talk about the direction of some plane or some little patch slanting in space is to use a normal vector. The normal vector was a vector that was orthogonal to the patch. And then we tried to figure out, well, how would we get a vector that's orthogonal to the patch and know for sure that we are looking at a vector that's orthogonal to the patch? Well, one way is to find two vectors that are in the plane or the patch that are not parallel, and then find a vector that's orthogonal to both of those at the same time. So now you might wonder, well, how would we go about finding such a vector? Well, that is what the cross product is about. The cross product is going to help us find such a vector. Okay, now we are going to require certain things of the cross product. And these are the things that we're going to require. So this is pretty much the definition of the cross product. Okay, so I know that I want to find a vector that's orthogonal to two other vectors, but I'm going to require that it behaves in a certain way. Namely, it has the magnitude that is the same as the area of the parallelogram formed by the two vectors. Okay, so if n is a unit normal vector, it's right here, n is a unit normal vector, then the cross product, we call this A cross B, again, we don't say times, we say A cross B versus A dot B, is going to be a vector in that same direction. However, the magnitude of that vector is going to be given by that. Now we saw yesterday that if I have a vector A and a vector B, then if I were to find the area of the parallelogram, if I form a parallelogram by those guys, and I find the area in here, the area is going to be the magnitude of A, magnitude of B, sine theta. The cross product is going to be a vector that is orthogonal to both A and B at the same time, and it will have the magnitude that is the same as the area of the parallelogram. Okay, so that's the guy we're going to want to find. Okay, now why would that be the guy we want to find? It turns out that having a vector that has this particular magnitude being orthogonal to both two other vectors happens to be highly applicable in other situations. There's also a very poetic reason for why you'd want a sine theta here, whereas the dot product would measure a cosine theta. And for that, you can actually read this link here, but you don't have to. But in case you're curious and you're wondering, well, why would we want this particular magnitude? There's some arguments given here. So yeah. Now, it's also worth mentioning that the cross product as we will define it will only work in R3. So specifically A1, comma, A2, comma, A3, cross product with B1, comma, B2, comma, B3. There is a generalized version of a cross product. It's called a wedge or an exterior product. You can see here for more info on that. But to be honest, this is way above our pay grade. If any of you become math majors, then you can come back here in like 2 years and read that link and you'll understand everything. Chances are if you were to read that now, 95% of it is going to go over your head because you just haven't covered enough math to actually fully understand that. So right now, just take it that we are just going to do this kind of vector in 3 dimensions only. All right. That being said, I want you to notice some things are immediate. 1, the cross product is a vector. So it is a vector that's orthogonal to 2 other vectors. There is a reason that I have it red, all caps, in a larger font, bolded with a bunch of exclamation signs on it. You need to remember the dot product is a scalar, whereas the cross product is a vector. So dot product works in any dimensions. It takes 2 vectors and it outputs a scalar. That scalar is related to the angle between the vectors. It's a measure of how much in line the 2 vectors are. The cross product takes 2 vectors and outputs a 3rd vector. That vector will be orthogonal to both vectors in the product, and the magnitude of that vector will be the same as the area of the parallelogram formed by the 2 original vectors. This immediately gives us something. The magnitude of A cross B is going to be the magnitude of this expression, which is of course going to be the magnitude of A, magnitude of B, magnitude of sine theta. This immediately gives you the following fact. If your theta is 0 or pi, then the magnitude of the cross product is going to be the 0 scalar. Which means if your A and B are parallel, the cross product will be the 0 vector, or respectively, the magnitude of the cross product will be the 0 scalar. So we can add 2 things to our maxim that we had before. This is a very important box right here. You need to know that. So these are just things we know now. When we're talking about vectors in space, dot product equals the 0 scalar means the vectors are orthogonal. If one vector is a constant times the other, it means the vectors are parallel. Another way of talking about parallel is with the cross product. A cross B equals the 0 vector means the vectors are parallel. And the magnitude of A cross B being the 0 scalar means the vectors are parallel. So now we have certain criteria that we can measure whether vectors are orthogonal or they are parallel. And so this box is very important. You need to know this box. Students often forget this box. Do not forget this box. You need to know this box. Muy importante. All right. Now, another thing you would notice is that there are 2 possible candidates for the role of the cross product. Okay. So if I have a vector here, like a vector A, and over here I have a vector B, there are actually 2 vectors that I could think about that would be perpendicular to both, aka orthogonal to both, and has the magnitude of the area of the parallelogram. Well, it could be pointing in this direction, or it could be pointing down in that direction. So now, for the sake of convention, what we do is we actually pick one. So whenever someone mentions a cross product, there is a specific one of these 2 possibilities that they have in mind. And we pick one based on the right-hand rule. This is not the right-hand rule from physics. If you want to know about the right-hand rule from physics when you get to electromagnetism, the link is right here. It's also not the right-hand rule from Calc 1. This is a completely different right-hand rule. This is the right-hand rule that tells you how to find the direction of a cross product. So this is how it works right here. Can I move these? All right. So here's how the right-hand rule works. The right-hand rule is going to tell us how to find A cross B, right? So we have A cross B right here. This is a cross here in case you can't see it, A cross B. if you take your right hand, there are two ways you can measure this rule. Point your index finger in the direction of A, stick out your middle finger, that will be in the direction of B, then A cross B will be in the direction of your thumb. Another way you can do it is to first stick your hand out straight. Yeah. It's like a cartoon hand here. Stick your hand out straight in the direction of A. Make a fist by curling your right hand in the direction of B and then stick your thumb up. That will be the direction of the cross product. Okay. Now in physics, this is actually the direction of the force of magnetism for an electromagnetic field, but you don't have to know that. This gives us the direction of the cross product. And actually, the physical interpretation of what this rule is why we want to define it this way. So there's a lot of things in the background here that we're skipping over. Okay, just to make sure that we know how to use the right-hand rule. For this diagram, okay, looking at this diagram right here. Looking at this diagram right here. Which one of these vectors would be A cross B? So is it n that's pointing up, or is it minus n that's pointing down? So there's, okay, hold on. Let me try something. Let me just take this opportunity to try something, some functionality that might come in handy later, since people might be too shy. It's a great reason to try this. Okay, boom, go. You guys see that? I just threw up a poll. Let's have a vote. Who thinks which one is what? Oh, look at this, they're racing. I don't know if you guys can see the bars moving in real time, but I can see it. And it's neck and neck. Okay, get your votes in, exercise your rights. It's actually neck and neck. Are you guys actually just randomly guessing at this point?
-10, because if you were to think about the
hold on,
product,
wait until the poll is finished. There's 3 people left to vote. It's like 53 to 47% so far. So it's like split, like the class is split towards. Oh my God, did someone choose the option just to get an even 50-50 split? I feel like, you know,
it's
those
like a
people who
debate.
literally.
Honestly, this is like a debate, a presidential campaign. Who's going to be elected for the president? Positive N or negative N?
Right, well, except it's not, because there is a rule that we have to obey here. So, Jason, can you tell us which one is the right answer and why?
I would recommend, you know,
Who would you endorse? Who would you endorse? Who's endorsed by
look,
Jason here?
IJK. Honestly, if you were to think about cross product, honestly, you would have to, cross multiply. And obviously, if you were to think about the standard form of IJK, it would be I minus J plus K. So you would determine that the whole, and you're trying to say that the N is the general vector. So I would assume it would be
I just
negative
want you to tell me, is it positive N or negative N in this picture?
negative N. That's
Why?
what I'm assuming.
Why?
As I said, if you were to think about cross product, honestly, you would have to think about, the IJK to notation. You know,
Yeah, you're
I
thinking
plus
way too
J plus
complicated.
K.
The answer is this guy.
I
It's
can do
minus
it.
n.
That's what I said. That's why it's negative n.
Right, but
I said
I
negative
wouldn't think of it in the way you're thinking of it. It's literally because in order to do the right hand rule, you would have to turn your right hand upside down. If you actually try, you'll realize you'd have to turn your right hand upside down. Yeah. Undo. You'll have to turn your right hand upside down. I'm having too much fun. Okay, you'll have to turn your right hand upside down in order to, so if you point it in the direction of A, you would have to turn your right hand upside down to curl your fingers in the direction of B. And your thumb would point down to get to the direction of A cross B. So it's the right hand rule. Like you literally have to have your right hand turned upside down in order to get that. So here, notice that if A was here, you point your index finger in the direction of A, curl your fist of your right hand in the direction of B, your thumb would stick up. To do that same thing here, you would have to literally turn your right hand upside down in order to get that. Now, of course, that automatically gives you the fact that the n here would be minus A cross B. And in fact, you would notice that that is in fact B cross A. So now that's what we'd have. Okay, so we're piecing together what a cross product has to behave like. We know the properties we want it to have, and now we know exactly what direction we need it to actually point into. Okay, so now here is the guy. So this is the guy. The area here is going to be the magnitude of A cross B. It will point up, and it will be a vector that is orthogonal to B and at the same time orthogonal to A, obeying the right-hand rule, and its magnitude will be the size of A cross B. It will be the area of the parallelogram formed by the two vectors. So that's what a cross product is. By the way, you can now get that these properties must be fulfilled. In fact, the first property I kind of justified to you by the right-hand rule already. A cross B is the same as the negative of B cross A, because if you turn your right hand upside down to switch from one to the other, you'd realize that one will give you the negative of the other. And so if you take the cross product in the opposite order, you actually get a negative sign. So that's important. So this tells you that the property one shows you the cross product is not commutative. So it's not like a dot product. Okay, cross product is not commutative. Also, I do want you to pay attention to this, something else that the dot product would work with, but the cross product does not. The cross product is also not associative. So I don't want you to think that this was left off in that box over there. It's actually on purpose. What does associative means? It means you can't just move brackets and everything stays the same. Basically, if I take A cross B and then cross C, it is not the same as taking A and then crossing it with B cross C. If I move the parentheses over, I don't get the same thing in general. It also should be obvious that A cross the zero vector is the zero vector. Hopefully that's also obvious. But all these properties take effect with the cross product. I'm actually going to use some of these properties later on. One property that's important, it's called the property 5 in this table. It's called the scalar triple product, or the box triple product, or the triple scalar product, or the triple box product. Whatever, you get the idea. You can call it by a bunch of different names. It's actually a way to find the volume, the signed volume of a parallelepiped. This is a parallelepiped. If I have vectors A, B, and C spread out in space, if I put all of them at the same origination point, and then I create a parallelogram with the A and the B, and with the B and the C, and the A and the C, and then I create a three-dimensional parallelogram, this is called a parallelepiped. And in theory, you can do this in higher dimensions as well. So you can talk about the n-dimensional parallelepiped. It turns out that the cross product, you can use a formula for involving the cross product that will actually give you the signed volume of such an object. And we're actually going to use this later on to figure out the volume of something that looks like this. Okay, so, and you can use trigonometry and derive this, but I'm not going to go through it. Basically, you just change things to sine and cosine. Magnitude of A, magnitude of B, sine theta gives you the area of this. Then times the perpendicular height is going to give you the volume. And then you can realize that you can express the perpendicular height again in terms of trig functions, and you can eventually derive this formula. But that's a very important formula, and I'll give you a different way to talk about property 5 later on. Now let's compute. Oh, that's actually wasn't a typo. Now let's get to the nitty-gritty. How would we compute the cross product in terms of components? So let's say I'm actually given two vectors, a1, a2, a3. Where are they? And b1, b2, b3. Can I find the components of the cross product? That's our next goal. How can I find the components crosswise? Well, there's a nice little mnemonic that works in our three-dimensional space, like the following. So remember we spoke about basis vectors yesterday, I, j, and k. It turns out with the right-hand rule applied on 3 space, like right here is an illustration, I can figure out the following relationships. I can figure out that I cross j is k cross k is I cross I is j cross I is minus k cross j is minus I cross k is minus j. You can remember that by this little circular mnemonic right here. Going around this circle clockwise gives you the positive cross products. For example, I cross j would give me k, j cross k would give me I, k cross I would give me j. Together, the negative ones go around counterclockwise. So for example, k cross j would give me I cross k would give me j cross I would give me k, right? So we can figure out these relationships here. Also, based on what I did above, you should realize that I cross I and j cross j and k cross k, these guys are all zero vectors. Why? Because remember, if I have two vectors that are parallel, then their cross product is the zero vector. So the right-hand rule gives us all these relationships. And these guys I know based on the fact that I is parallel to I, j is parallel to j, k is parallel to k. So now I'm going to derive for you how you would find the components of a cross product. So suppose we have 3 vectors, a1, a2, a3, and b1, b2, b3. How do we find the cross product? Well, let's actually derive it from scratch putting together all the concepts that we have seen thus far. This here is going to be a1i plus a2j plus a3k cross with b1i plus b2j plus b3k. We're going to figure out what formula this must have. Now, by the properties, I know the cross product obeys the distributive law. That's property 3 up here, right? So I know that. So what I can do here is I can literally just distribute. I can take this and multiply out, then take this and multiply out, and etc. I can distribute. What would that give me? I would have A1, B1, I cross I. Plus, I would have A1, B2, I cross J. Plus, I would have A1, B3, I cross K. Here I'm using properties 3. That tells me I can distribute, as well as property 2, which tells me I can factor the constants and move them all in front. Now distribute with the A2s. A2B1 times J cross I, plus I can have A2B2 J cross J, plus A2B3 J cross K. Plus distributing the A3s, A3B1 K cross I, plus A3B2 K cross J plus A3B3 K cross K. Now, let's see what all these guys are. I don't know if we can actually fit that page. Maybe I'll reduce the size a little bit so we can actually see. Okay, so I'm going to be using this, what's in this diagram right here. Now, of course, we know that I cross I is going to be 0. So that's the 0 vector. So that's going to give me a 0 vector there. J cross J is also 0. K cross K is also 0. Okay. What about the I cross J? From that diagram, that would give me K. What across the I cross K? From that diagram, that gives me minus J. What about the J cross I? From that diagram, that gives me minus K. What about the J cross K? From that diagram, that gives me I. What about the K cross I? That would give me J. What about the K cross J? That would give me minus I. And that's that. Now what I'm going to do is I'm going to group these guys. So let's group the I's. Let's group the J's. And let's group the K's. And that's actually going to be what the cross product looks like. So what is attached to the I's? So I'm going to go over here and check out all the I's. So here I have an A2B3 minus an A3B2. For the J's, I have a negative A1B3. And in fact, just to make it coincide with a formula, a mnemonic that I'm going to give you later, let's factor out a negative here. So I'd have A1B3 and the other J's here, A3B1 minus A3B1. For the K's, I have A1B2 minus the other K, negative K, A2B1. And there you have it. This guy is the cross product. A2B3 minus A3B2, comma, minus A1B3 minus A3B1, comma, A1B2 minus A2B1. And voila, there you have the cross product. This here is your A cross B, component-wise. So if I know the components of A and B, I can actually find the vector that is going to 1. It will be orthogonal to both A and B at the same time. 2, it will obey the right-hand rule. And 3, the magnitude of this vector will be the same as the area of the parallelogram formed by A and B. Now, there's another way to derive this to go back to the foreshadowing, by making the aesthetic choice. You could also do this by pretending that your cross product is a vector C, C1, comma, C2, comma, C3. And what you would do is you would dot product it with A, dot product it with B, and you would get a system of equations. And by going through and making the aesthetic choices to get all of these guys equal to 0 components, you can actually derive this formula as well, right? But that is a little bit haphazard, because how you can't describe the aesthetic quote unquote choice in general. So this is actually a straight up bare bones brute force way to actually compute the cross product. Now this you need to actually memorize. Now, before you freak out, don't worry, there's a mnemonic. So a lot of you knew this was coming. There's a mnemonic to remember that. So while you do need to remember it, you don't need to remember this formula. I am actually going to teach you a mnemonic so that you can actually remember this without actually just memorizing that. But of course, there's no harm in memorizing this. But if you're like me, I wouldn't want to memorize that. I would rather know some sort of process where I can get the answer easier. Now, Those of you who've computed cross product before knows what I'm going to do, but for the benefit of those who don't know, I'm actually going to have to talk about something called a determinant. Okay, so let's do that. Now, to be clear, we're going to cover determinants. It will not be comprehensive, so don't think you can go into a linear algebra class with what I'm going to tell you and you'll be fine. You will not be fine. So what I'm going to do is give you a bare bones treatment of determinants. I'm going to tell you the need to know. I'm going to tell you everything on a need to know basis, and you're going to use this to be able to compute determinants. For this class, you won't need to know anything larger than a 3x3. In a general linear algebra class, you'll need to know a lot more. So let's actually jump into it. So for a while, I'm going to deal with something that seems completely not related, but I'm going to tie it back into the cross product presently. So, okay, first you need to know what a matrix is. A rectangular array of numbers with m rows and n columns is called an m by n matrix. It's read m by n matrix. For example, this here is a 2x2 matrix. This is a 3x3. This is a 2x3. This is a rectangular array of numbers. It has 2 rows, 2 columns, therefore it's a 2x2. This has 3 rows, 3 columns, therefore it's a 3x3. This has 2 rows, 3 columns, therefore it's a 2x3. These are what we call each of these are called a matrix. The plural is matrices. I don't know, you don't need to know that, but plural matrices. Now these guys are remarkably applicable. So applicable, you wouldn't believe how applicable these guys are. The Google search engine runs on matrices. A lot of AI technology runs on matrices, machine learning. It's a lot about matrices. So these things apply to things that you wouldn't even begin to realize, right? When people are trying to program AI assistants like Siri and Google Assistant to actually sound human when they speak, they actually use matrices with probabilities in it. Like the applications are vast and they're mind-boggling. We're not going to need to know any of that. So there's also a number associated with the H matrix. Not with any matrix, with square matrices. These are the ones that have the same number of rows and columns. There's a number that we can measure the area of the hypervolume of the parallelepiped formed by them. So for example, in here, if I have the vector with components a comma b and the vector with components c comma d, if I were to find the area of this guy, this is going to be plus or minus the determinant of the matrix. Okay, so the determinant is a measure of area. And if I have a 3x3, so the area is going to be that. If I had 3 vectors, and I can form if I had 3 vectors, like here was my 1 vector, here's another vector, they can form a parallelogram. Here's a 3rd vector, this can form a parallelogram with that, this forms a parallelogram with that, this goes across here, this goes across there, this goes across here. Then the volume of this is the determinant of A, plus or minus, right? Where in this case, A is a 2x2, and in this case, A is a 3x3. Okay. And the rows are the components of the vectors. So that's what this number is. You don't need to know that really. What you do need to know is how to compute them. So let's say I have a 2x2 matrix here, A, B, C, D. The 2x2 determinant is given by this expression here. In other words, if I take this times this, and I subtract that times that, I get an expression called the determinant. This is actually going to be the area of the parallelogram. So, for example, if I ask you, what is the determinant of 1, 2, 3, 4? Well, this is going to be equal to, I would take the 1 times the 4, and then subtract the 2 times the 3. So this would be 1 times 4 minus 2 times 3. This is actually going to give us minus 2. So that is the determinant here. And what does that minus 2 represent? Well, if I had a vector which is 1, 2, and another vector which is 3, 4, of course not drawn to scale, and I wanted to find what is the area here, the area is 2 squared units, right? So, okay. But that number associated with this matrix gives you that physical property. Okay, but that's how you do it for a 2 by 2. Okay, cool. Let's move on to 3 by 3. So to figure out how to do it for a 3 by 3, this is the important one. We need to first know how to do it for a 2 by 2, and I just told you how to do it for a 2 by 2. Now we're going to learn how to find the determinant of a 3 by 3 matrix. We're going to use a technique called Laplacian expansion, and I'm going to use one variation of Laplacian expansion. The Laplacian expansion for a 3 by 3 technically will have 1, 2, 3, 4, 5, 6 variations, but I'm only going to teach you one. It's always going to be the one that you're going to do. So let's say I had a 3 by 3. A, B, C, D, E, F, G, H, I. So here's how we can compute the determinant by Laplacian expansion. First of all, in general, you can choose any row or column to expand along, but I'm going to teach you how to expand along the first row. So we're going to expand along the first row. Now, you're going to attach a positive sign to the A, you're going to attach a negative sign to the B, you're going to attach a positive sign to the C, and it's always a positive sign top left. Okay, so even if I wanted to run these signs along some other row or column, for example, the second column, I could just start with a positive on the A, move over to the B, it's negative, then this would be positive, that would be negative, right? So, but in general, let's just keep it in the first row. Here is how you would compute the determinant. You're going to follow these signs. So you're going to have a positive A, and you're going to multiply that by a 2 by 2 determinant. Then you're going to have a negative B. You're going to multiply that by a 2 by 2 determinant. And then you're going to have a positive C. And you're going to multiply that by another 2 by 2 determinant. And I'm going to tell you which 2 by 2 determinant specifically in a little bit. Move the chat box out of the way here. So here's how we're going to find these determinants. So to figure out what is attached to A, you're going to take the matrix A, B, C, D, E, F, G, H, I. You're going to block out everything, if you're focusing on the A, block out everything in that row and that column. The matrix that you have left over is what goes in here. So here we would have E, F, H, I. Okay, and that's just a 2 by 2 determinant, which you can just use this little cross product difference to actually, cross product is a bad, it's a bad way to call that, but you get the idea. Now to find the B, you're going to actually do the same thing. So in the case of the B, A, B, C, D, E, F, G, H, I. Focusing on the B, I'm going to block out everything in that row and that column. I will have a matrix left over here. And that is the guy that I put in the B. So here, I would have D, F, and it's very, very long-winded to explain, but once you actually get the hang of it, it's actually really quick. A lot of you will be able to even do a lot of what I'm talking about in your heads after a while. Now, if it's the first time you're seeing it, it might be like, what the hell is going on? But trust me, it'll eventually become very easy. A, B, C, D, E, F, G, H, I. So focusing on the C, block out everything in that row and that column. You'll have a matrix left over here. That's the guy that goes in here. So here you'd have D, E, G, H. And with that, we can now actually finally compute the 3x3 determinant. It's going to be A times EI minus FH. Minus B times DI minus FG. Plus C times DH minus EG. And that's how you would find a 3x3 determinant. So you can even take a picture of that. And I will, we're going to do, wait, let me move this up a little bit. Take a picture of that because we're going to use it. Now, those of you who know about how to find determinants already, you will actually know this process, but I'm explaining it from scratch for those who have not taken linear algebra, you've never seen a 3x3 determinant. Now you kind of know. So I have an example here that I want you guys to do. So let's find this 3x3 determinant right here. Okay, so again, we're going to expand along the first row. So I'm going to look here. Plus sign, minus sign, plus sign. So this is going to be +1 times some 2x2 minus a -1 times some other 2x2 plus 2 times a 2x2. Okay, so someone who probably has never seen a 3x3 determinant before, or you're a little bit shaky on what I just said, maybe you can try to tell me what would be in this one, in that one, and in that one. Let's start with the first one and tell me the numbers along the first row, then the second row. So what would I fill in here? Three, 1, and then the second row, 1 minus 1. Right, good. Okay, second matrix, what would go in here? First row. 0, 1, yeah, second row. Right, 1 minus 1. Okay. Third one, first row. 0, 3, second row. 1, 1. Okay, so hopefully we're getting it. All right, now you just do that 2x2 determinant. So you're going to this times this minus that times that. And you're going to do that for each of these guys. This times this, and then you're going to correspondingly subtract that times that times that. So now, what would we get? Well, we'd have 1 times 3 times minus 1 minus 1 times 1. Plus 1 times 0 minus 1 times 1. Plus 2 times 0 minus 3 times 1. So this is going to be -3 minus 1 plus, this is going to be -1 plus 2 times -3. So this is going to be -4 minus 1 minus 6 minus 11. And that would be the determinant. One way you can interpret that -11 is if I were to take these 3 vectors and not to scale, of course, not to scale. If I were to take these 3 vectors, like 1 going across here, 1, 1, -1, there's another vector going across here, that was the 0, 3, 1. And there's another vector pointing here, and that is the vector 1, minus 1, comma 2. If I were to create a box, or quote unquote, a parallelepiped, then the volume of such a box would be 11 cubic units. Okay, so that's the physical interpretation to this number, but that's how you'd actually do the computation. And that's how you can find a 3 by 3 determinant. Okay, so hopefully that's clear. With a lot of practice, you'll actually get very quick with doing this. So if you're kind of shaky right now, do not worry. Going through like a single set of homework problems can actually get you up to speed with that relatively quickly. All right. Now, why did I teach you all that? Well, I taught you all that to be able to say this right here, essentially. This now gives us the power to compute a cross product to figure out this formula right here in a very nice way. In fact, with the above, we can now define the cross product in a different way. We can now define the cross product as a 3 by 3 determinant. If I know the vector A is A1, comma A2, comma A3, and the vector B is B1, comma B2, comma B3, then the cross product A cross B is given by this. It's a 3 by 3 determinant where along the top row are the basis vectors, I, J, and K. Across the second row is the vector on the left, which is the A, so it's A1, comma A2, comma A3. And across the last row is the B1, comma B2, comma B3. You will notice that if I were to apply the rules of determinants that I have, this is going to be plus I times, block out everyone in that row and that column, and then do the multiplication, you would get here A2B3 minus A3B2 minus J, block out everyone in that row and that column, you will get A1B3 minus A3B1 plus the K, block out everyone in that row and that column, you would get A1B2 minus A2B1. And gasp, that's the guy we had before, right? That's the guy we had when we actually painstakingly derived the cross product the first time. Same guy we got before. You can even compare it to what we had up here. It's the same thing. So teaching you determinants is basically just me teaching you a short way to find a cross product, right? So it turns out that the cross product is actually connected to the volume of, it's kind of like a weird kind of volume, believe it or not, which kind of makes sense because a volume is just an area with another dimension attached to it. We already know that the magnitude of the cross product gave you the area of the the area of the parallelogram formed by two vectors. And yeah, all right. As far as who came up with this stuff and why, how they did it, well, necessity is the mother of invention. Basically, I described a need that we had last class, which we needed to be able to find an orthogonal direction. There are also areas in physics where we would like the orthogonal direction to have the magnitude of the area of the parallelogram. So basically, they constructed it the same way I did. They know that this was the guy they want, and they derived all these properties using trigonometry of how that guy would have to behave. They came up with a right-hand rule that coincides with electromagnetism, and taking all of this to its logical conclusion, you can literally use the distributive law to figure out that this guy would have to happen. Now, simultaneously, people were studying determinants because they're super important, and you realize, hey, that pattern is actually the same pattern that we needed up top when we're trying to talk about cross products, and voila, you never know. Once you actually need something, people figure out things when they need it at the end of the day, and boom, there we have a nice way to compute the cross product. Now, let's end this section with some examples. boom, boom, boom. This one is underlined. So we're going to do these examples here. All right, so let's talk about this. Here are two vectors. There are two 3x3 vectors, three-dimensional vectors. Find the cross product of A and B. Namely, I'm talking about A cross B, right? So I want to find A cross B. Now, once you know you want to find that, you're going to set up this setup right here, I, J, K. Then you're going to line up the components of A across the second row, line up the components of B across the third row. And now you're actually going to do that process that we did before. So based on the first component, second component, third component, and the second component, you know, you're going to put it in negate that. So what goes into the first component? Well, you're going to block out so you're going to block out the I rows and columns. You'll see you have a matrix here, 2, 3, 0, 2. You're going to do that multiplication across diagonals. So it's 2 times 2 minus 3 times 0. So here we have 2 times 2 minus 3 times 0. We're going to do the same thing in the middle. For the J, block out everything in that row and that column. You will have the matrix 1, 3, second row is 3, 2. Then we're going to take 1 times 2 minus 1 times 2 minus 3 times 3. Then for the K, you're going to block out everything in that row and that column. You're going to notice that this matrix is left over. And you're going to, again, do that thing with the diagonals. 1 times 0 minus 2 times 3. And that here would give you 4. This will be minus 9 plus 2. It's minus 7. And then you take the negative of that, so it's positive 7. And then here we would have minus 6. And that is the cross product. So based on everything that we've talked about before, what are the properties of this vector? Notice here that if I were to take the vectors 1, 2, and 3, let's make this a little bit shorter so you can see. 1, 2, and 3. And again, not to scale or anything. If I were to take a vector that goes like A and B, then A cross B would be the vector pointing up like this. This is A cross B. And that would be the guy that we just found. This would be the vector 4, 7, minus 6. On top of that, if I were to construct a parallelogram by these two vectors, and I want to find the area of that parallelogram, the area is going to be the magnitude of that vector. That's going to be the radical of 4 squared plus 7 squared plus 6 squared. And I don't know what that is, but you guys can compute that. So that is finding the cross product of the two vectors. Another thing is it's going to be orthogonal to both the A and B at the same time. And its magnitude is going to give you the area of the parallelogram formed by A and B. Well, a normal vector is how you would measure the direction. This would be the direction that I claim as the direction of the patch. if I tell someone the thing is slanted in 3 space based on this normal vector, everyone would actually know exactly how this thing is slanted. This vector and its negative, and any scalar multiple of it, is actually going to tell you the direction of the slant. Because nothing parallel would work, and nothing pointing out at any angle other than 90 degrees would actually work. And I physically showed you an example of why that was the case yesterday. But yeah, that would be the cross product. Just do that little calculation, and Bob's your uncle. All right, let's try this one. Find a vector orthogonal to the plane that passes through these 3 points. So these are points now. What are the, that's size 16, that looks a little bit small. Let me make this bigger. Okay, so here is the idea. I have a plane, and I know in that plane there are 3 points. There's a P, there's a Q, and there's an R. I want to find a vector that's orthogonal to this plane. Want this guy. Idea is how we would go about finding such a vector. So I know I have a plane. I want to describe its direction. But the only information I have so far is actually just what 3 points are in the plane. Tell me some ideas on how I can find the direction that this plane is slanted if I know 3 points. Ideas.
Could you use a dot product?
To what end? How would you use the dot product? What would you try to get from it?
So what you would do is that you would find 2 vectors. So the 2 vectors I would do is QP and QR.
Okay.
And then from there you can determine if the vectors are orthogonal. And if they are, then you have your plane. And that's all that I
Figure
got
out
so
which
far.
vectors are orthogonal.
QP and QR.
Well, these 2 vectors here are parallel to the plane. It doesn't matter if they're orthogonal or not, actually.
Oh.
These guys are in the plane. The green vectors are in the plane. I want to find the vector that's poking out of the plane at a right angle.
Oh, okay.
But this isn't a bad start, believe it or not. I could actually use the 2 vectors that you just constructed to get to the answer. Based on what we were talking about yesterday, if I know 2 vectors in the plane, then I can find a vector that's orthogonal to the plane by doing what? What kind of vector do I need to find? So I can definitely find those 2 vectors. QP and QR, I can definitely find them. What would I do with them? A vector projection? Well, that would give me another vector, right? If I project one onto the other, that just gives me another vector that's in the same direction as one of them. Like, what does that help me with? I would just find another vector that's parallel.
I would recommend to subtract, like, from the Q to the P, subtract like each of them, like PQ and PR. So 3
Yes,
minus Q.
that would be finding the actual vectors. So PQ, let's actually just find them. If I want to find PQ, what would the numbers be? What would PQ be?
Subtract from Q to P, like, 3
Yeah.
minus 2 is 1, 1 minus 0 is 1, and 0 subtract -3 is +3. And same thing goes to
No.
the,
QP. If I'm finding QP, how do I find that?
oh, then 2 subtract 3 is
Right,
-1.
final minus initial. So it's -1, comma.
So it's like, it's a PQ. Aren't you asking for PQ?
I'm doing QP. I mean,
Oh,
PQ
QP.
would be aesthetically nicer, but someone already suggested PQP. It doesn't matter, actually.
We could do the aesthetic option too.
Yeah, it won't matter, though.
Okay.
It won't matter.
No, it won't matter, but Jason doesn't like it. Let's change it. Okay, let's say we go PQ and PR, because, if we just go in the same direction as the alphabet would have gone in. Okay, so this is final minus initial, the coordinates of Q minus the coordinates of P. This would be 3 minus 2, comma 1 minus 0, comma 0 minus a minus 3. So that's that vector. This vector here will be the coordinates of R minus the coordinates of P. 5 minus 2 is 3. 2 minus 0 is 2. And 2 minus a minus 3 is 5. So those are those vectors. Okay, so we can find the vectors. Not a big deal. Okay, so these are PQ, which is 1, 1, 3. And then I have PR, which is 3, 2, 5. Okay, I can find the two vectors. What do I do with them? How do I use them to get to the guy that I actually want? I want a vector that's orthogonal to the plane. What relationship would such a vector have to the vectors PQ and PR? Parallel. Do we remember what parallel means? If I find a vector that's parallel to PQ and PR, it will just be another vector in the plane, because it will be in the same direction, right? It'll just also be a vector in the plane. Okay, do you guys remember that thing I did yesterday with the book? We figured this out yesterday. Was everyone as out of it as I am? I was. Or maybe you guys aren't visualizing. Okay, let's go again. This is the plane. We just created two vectors in the plane. Right? My goal is to find a vector that does this. How does this black vector relate to these two vectors that are in the plane? Is it parallel to them? It's perpendicular. It is orthogonal. Okay, so if I care about this black vector, I need a vector that is orthogonal to this one and at the same time orthogonal to that one. Do we know how to find such a vector?
Once you subtract, each of them, PQ and PR, just find, the cross product, simple as it is.
Why did he say subtract when he said find the cross product?
Once you subtract and get PQ and PR, find the cross product. Simple as it is.
Right. So find the cross product is the answer. It's literally what I've been talking about for the past hour. Find the cross product. Right. So once I have these two vectors that are parallel to the plane, their cross product is going to be orthogonal to the plane. Right. So to find this guy, what I could do is just take PQ cross product with PR is a candidate for this guy. Right? This was the whole point of what we were developing like this whole time, right? We wanted a way to find a vector that is orthogonal to two other vectors. Right? Once I know two vectors are parallel to a plane, then any vector that's orthogonal to those vectors will automatically be orthogonal to the plane. Right? So a way to find a vector that's orthogonal to the plane is to find two vectors in the plane and then take the cross product. It's one of the best uses of the cross product, at least in the Calc 2 context, right? So PQ cross PR can serve as the vector we want. So that's what I'm going to do. So I'm going to find PQ cross PR. Let's call this N for normal vector. That's just going to be IJK. And then I'm going to put PQ across the first row, PR across the second. And it really doesn't even matter what order you did, if you did these vectors in the opposite order, and if you put these rows in the opposite order, because the worst case scenario, you can get the negative of the answer. You can get the answer that's going down here. But so it really doesn't matter. It'll still be orthogonal. And now we know how to actually compute this. You should be able to do it in your head after a little while. So this is going to be 5 minus 6. The middle term is going to be, and you can even skip writing the negative sign, just do the diagonal in the opposite way. 9 minus 5. And then 2 minus 3. And that's going to be your guy. That is a vector that is orthogonal to that plane. No, it's the negative of 5 minus 9. If you look back at the formula, there's a negative sign here. Right? It comes from this sign change here, which to explain to you why the sign changes in that particular fashion, I'd have to do too much linear algebra for you guys. That's not the point. There's a negative sign change in there. For the middle term, there's a negative sign change. Okay, so this is one use of a cross product. If I find two vectors that are in a plane and they're not parallel, I can actually find a vector that's orthogonal to the plane by taking the cross product of those two vectors. This is very useful for talking about the direction of the plane. Here's another one. Here's another example. Right, so as I mentioned before, it doesn't matter which vectors you pick and in what order you do them. It actually doesn't matter. So we could construct the vectors differently. and cross in any order. And we would get equivalent answers. So I have the plane. We did this vector and that vector, connecting these 3 points. Connecting these 3 points, I could have done this vector and that vector. I could have done this vector and that vector. It doesn't matter because these vectors that I'm constructing, again, they will necessarily be parallel to the plane, which means when I take their cross product, I would necessarily get something orthogonal to the plane. Right? It's not, the order isn't going to matter. Like our calculations guarantee that when you take a cross product of these 2 things, any 2 things that are parallel to a plane, you will get a direction that's orthogonal to the plane. You're going to get the plus or minus of this vector, regardless of which one you constructed.
Professor, what will happen if a student puts -1i plus 4j minus 4? Okay, what will happen if a student puts -1i plus 4j minus 1k?
Nothing. These are equivalent answers.
But you said vector of n equals, vector brackets -1, comma 4, comma -1. But if a student puts
it's
an
exactly,
ijk notation, what's going to happen?
Nothing's going to happen. It's exactly the same thing. It's like me telling you that the answer is a half, and then you're asking me, what if a student wrote down 0.5?
0.5?
It's the same thing. Like nothing would happen. It's just that now you know that if I gave you the answer as multiple choice, if you wrote it down as -i plus 4j minus k, and in the multiple choice, the answer is the bracket -1, comma 4, comma -1, you should recognize that it's the same as your answer, and you should pick that option. Other than that, if you wrote the ijk notation, it's the same. There's no difference. What would be a problem is if you wrote the ijk notation and then you put the angled brackets on top of that and you mixing notations, that's bad. So that you don't want to do. But other than that, it's the same thing. Personally, the only reason why I write down this notation as opposed to the ijk, it's actually harder to write down the ijk notation in general. It takes more strokes of the pen. So statistically, this is the conservative way to write a vector in terms of the amount of work you have to do when writing down something. Find the volume of the parallelepiped formed by these guys. So what does that mean? So not necessarily accurate. For illustration purposes only. But basically I'm just saying, okay, so I have like a vector like this, a vector like that, and a vector like this. And essentially what I want to do is create this guy, the kind of guy that we were talking about earlier. Okay, and I want to want the volume of this. It's called a parallelepiped.
Parallelepiped.
Okay, so that's what we want. What is the volume of that parallelepiped? It turns out that the volume is going to be the magnitude of the scalar triple product. What is the scalar triple product? This was the thing that was written about in the property up here. Boom. I don't know. Why is it called a parallelepiped? It's just that's getting too much into the etymology of the word. Basically, It's the kind of like a parallelogram, but you want a higher dimensional analog of a parallelogram. For whatever reason, they call it a parallelepiped. I don't know why it's called that. It's just called that. Why is a parallelogram called a parallelogram? Why is it called parallel in the first place? Just an oddity of language. So that guy was described in property 5 in that table above. Basically, this is going to be A dot B cross C, and then take the magnitude of that. What this looks like is like, again, it's actually going to be a determinant where you put the vector A across the top. So the vector A is going to be, let's change these colors. Make this red. Okay, B is the red. I'm going to put that in the second row. A is the green. That goes into the top row. And C, let's make that guy blue. And blue, babo, dee, babo, da. So you pretty much line up the vectors like that. And you're going to find this determinant. And then you're going to take the magnitude of that determinant, just in case it's a negative number. You take the absolute values. So A was 1, 4, minus 7. B, 2 minus 1, 4. C, 0 minus 9, 18. All right, let's get some practice in. You guys actually do that. I'll give you 2 minutes. And this is the last example. So after this, we'll wrap up. Tomorrow's lecture is going to be interesting.
What's going to be interesting?
I was hoping tomorrow's lecture. I'm going to keep you in suspense as to what that is.
Well, what is it going to be, though?
I'm keeping you in suspense, Jason. Yeah, Jason's going to be up all night now. Anyway, what is this? Find that determinant. I'll give you guys 2 minutes to do it. What's it going to be, though? Okay, focus on that determinant. I want to make sure that everyone can actually find it. 2 minutes, then tell me the answer, and then we can get out of here. Kayla already has what she thinks is the answer. So the rest of you have a little less than a minute left.
According to what I'm assuming, it would be 0, because if we were to think about, like, you know, the cross product.
Kayla doesn't think she knows.
However,
hold on.
like,
Give the other people a chance if you have the answer. Just wait. Okay, so Kayla, Jason, Abdul Rahman, Natalie, we all think it's 0. Let's actually see if they're trying to fool us. All right, so we go in. Of course, there's absolute value around all of this just in case the answer is negative. So again, go along the first row. It's going to be +1. Then I'm going to have -18 plus 9 times 4, which is 36, -4. Then I'm going to have 2 times 18, which is 36, minus 4 times 0, which is 0. Then I'm going to have plus a -7. Then I'm going to have 2 times -9, which is -18. And -1 times 0, which is 0. And so that is going to be 18 minus 4 times 36 minus, well, plus 7 times 18. Well, 36 is 2 times 18, right? So this here would be 18 minus, this is 6 times 18 plus 7 times 18. So then we have 1 apple minus 6 apples plus 7 apples. No, that's 2, that's a 4, sorry. So this here is 8. So I have 1 apple minus 8 apples plus 7 apples. We have 0 apples. So the volume is 0.
It's
What is-
nada, nothing. Big
Right.
O.
Nada. What does this mean?
A Cheerio.
This means the vectors are what we call coplanar. So that's the terminology we would use for these. That means they all lie in the same plane. And so there is no volume. They all lie in the same plane. So there really is no parallelepiped. It's like there's a plane here and the vectors A, B, and C are all in that plane. So it gives us a 0 volume. So if I have 3 vectors in 3 space and I want to know if they all lie in the same plane, what I could do is the scalar triple product. If I get 0 as the answer, I know they all lie in the same plane. If I don't, then they don't. All right. So we will stop right there. And yeah, hopefully that was enlightening. So that was the cross product. Very important object, very important vector product. Do not mix up the cross product with the dot product. So dot product is a scalar. It works in any dimension. It's a scalar that helps you measure the angle between 2 vectors. Remember that A dot B is magnitude of A, magnitude of B, cosine theta. It's also the product of corresponding components added together. Cross product is a vector that only works in 3 dimensions. It will give you a vector that's orthogonal to 2 vectors in the cross product. So it's a vector. The magnitude of that vector will be the same as the area of the parallelogram formed by the 2 original vectors, and it obeys the right-hand rule. We can use these to find normal vectors to planes, which is going to be very important for tomorrow's lecture, actually, as well as many other reasons. For now, we'll stop there. Hopefully you guys enjoyed that. Hopefully you guys are doing well. Let's wrap up. I'll try to get the video up by tonight so Jason doesn't freak out, and we will end there. So thank you for stopping by. Good night, everyone. Stay safe, and I will see you in the next one. Ciao.